Okay, so there should be lecture notes on exponentials and logarithms for Math 112. We're starting with exponential graphs. So an exponential function, this is section 3.1. An exponential function is one of the form y equals b to the x. B here should be a positive real number. The exponent, the x, that's the variable, not the base. If the base is the variable, x to the n, that's a power function. Is that a tad better? Nice, it's as good as the focus gets. So the base b, we want to be positive, whatever your base is, because otherwise you get complex numbers. If b is -1, then if we take b to the 1/2, we get I, and we really don't want to deal with complex numbers in this. So what do graphs of exponential functions look like? They look like that, pretty much. This is the graph of y equals 2 to the x. What points are on that? Plotting some points is very nice. -2, -1, 0, 1, 2, 3. 2 to the 0, that's 1. 2 to the 1, well, that's just 2. 2 squared, that's 4. 2 cubed, oops. 2 cubed is 8. Right? So for positive numbers, that's not too bad. Remember that 2 to the -1, right? The negative power means put it down into the denominator. So 2 to the -1 is 1/2. 2 to the -2 is 1 over 2 squared, which is 1/4. So those are various points. X equals 0, y equals 1. When x equals 1, y equals 2. When x equals 2, y equals 4. 3, 8. Note that every time you increase x by 1, you double y, right? So if we go from 0 to 1, we went from 1 to 2. Going from 1 to 2 on the x-axis meant we went from 2 to 4. On the y-axis, 2 to 3 here, meant we doubled that there. Which means also if you go to the left, right, starting at 1, if you go left 1 unit, you cut it in half. So there's 1/2. If you go left 1 more unit, you cut it in half again, so 1/4, and you end up with 1/8 over there for everybody. So what's the domain of this? All x or -infinity to infinity. The range is only positive numbers, right? Because if you keep going to the left, you keep cutting the y values in half, but they never become negative. They always remain positive. And you never actually get down to 0. So your range is from 0 to infinity. Special points, 2 points to remember, 0, 1, and this point, 1, 2. And the horizontal asymptote is to the left. What a horizontal asymptote is you go out further and further to the left on the x-axis. The graph just gets closer and closer and closer to the x-axis, but never actually touches it. And so it's a horizontal asymptote. So this is pretty standard. All graphs, when you're asked to graph an exponential graph, what does it look like? It looks like that. Oops, sorry about that. It looks like that. This is the point 0, 1. And at 1, your y value is b, whatever that is, whatever your base is. And a horizontal asymptote, y equals 0 out to the left. So that's the basic exponential graph. 2 points, 0, 1, 1, b, where b is your base, and a horizontal asymptote, y equals 0 out to the left. So what about graphs where your base is a fraction, like b equals 1/2? But if you go back and look at the exponent stuff, the first video we did, 2 to the -3 is the same thing as 1/2 cubed. So 2 to the -3, that's 2 to the -1 quantity cubed, which is 1/2 cubed, which is 1 cubed over 2 cubed, which is 1 over 8. So 1/2 to the x, 1/2 is 2 to the -1. 2 to the -1 to the x, we can just multiply the x and the -1 together, and you get 2 to the -x. So graph of 1/2 equals y equals 1/2 to the x is the same as the graph of y equals 2 to the -x. Multiplying the x by minus sign that's inside the function that flips the graph over the y-axis. So this is y equals 2 to the x, that's this. This is y equals 2 to the -x, y equals 1/2 x, same thing. Right? We take the graph of y equals 2 to the x, you flip it over the y-axis to get the graph of y equals 1/2 x. So, right, 1/2 x, well, if x is 1, right, that's what you get from y equals 2 to the x flipped over the x-axis. So that's 1/2. This is 1. No matter what base here is, base to the 0 is 1. Base to the 1 is whatever the base is. And so going here to the right, we're actually going to be decreasing. We're cutting everything in half as we go out to the right. Going out to the left, we'll be doubling stuff. So 1/2 to the -1 is 1 over 2 to the -1, which is 2. Because the minus sign says take this, put it up in the numerator now, because it's minus sign in the power in the denominator. So this is 2 and this is 4. So domain, still all x, or in interval notation, -infinity to infinity. Range, y greater than 0, or in interval notation, 0 to infinity. Special points are still 0, 1, and 1, 1/2. Horizontal asymptote is y equals 0, but to the right now, because we're just declining out that way. So if you have a fractional base, the graph looks like this. X-axis, y-axis, goes through the point 0, 1, and goes through point 1, b. Horizontal asymptote, y equals 0, 2. So basically what graphs look like, right? It's standard thing we've done with all the graphs that we've introduced. What does the graph look like? What are some points? Domain, range, special points. So the graph can be moved around by transformations, just as other functions can be. We don't really need to be super careful about graphing these things. If we want to graph y equals 5x plus 2 minus 3, I'm not going to include a lot of detail. We just want to know what the shape is. So, oops, this is supposed to be a 5, not a 2. That's supposed to be a 5, not a 2. So we'll start with the graph of y equals 5 to the x. What does that look like? It looks like your basic graph. Goes through the point 0, 5, goes through the point 0, 1, goes through the point 1, 5, horizontal asymptote, y equals 0 to left. So what does my transformations do? X plus 2, that means we're moving it to the left 2 units. Minus 3 is down 3 units. So we want to know, where do my points go in my horizontal asymptote? So 1, 5, if you move it left 2 units, so 1 minus 2 is minus 1, 5, and then if we move it down 3 units, it goes to minus 1, 5 minus 3 is 2. What about 0, 1? 0, 1, move it left 2 units, so that means the x coordinate changes to minus 2. And then you move it down 3 units, so 1 minus 3, that puts me at minus 2, minus 2. My horizontal asymptote is y equals 0. Moving a horizontal line left to right doesn't change it at all. So get y equals 0. Moving it down, though, that does change it. So that'll be going down 3 units. So what does my new graph look like? 1, 2, 3. At minus 3, it's got a horizontal asymptote out to the left. It goes through the point minus 2, and it goes through the point minus 1, plus 2. So here's x equals minus 1 and plus 2. So horizontal asymptote out here, goes through this point, goes through this point, and goes up. So we just moved it left 2 units and dropped it down 3 units. And you can keep track of what it looks like by looking at the horizontal asymptote and the 2 special points. And the last thing is, here are 4 graphs. How can you tell which is which? So 2 to the x, 1.5 to the x. Here the base is bigger than 1. So these two graphs should look like this. 1/3 to the x, 1/4 to the x. The base is less than 1. So those two graphs should look like that. So these two must be these two, and these two should be those two. How do you tell which is which? Well, look at the base. The base is 2, so when x equals 1, this graph goes through y equals 2, so this must be y equals 2 to the x. This graph goes through 1.5, x is 1, y is 1.5, so that graph is 1.5 to the x. Is this one. So the bigger the base, the faster it grows to the right. What about for these two? Well, it's a little bit easier actually to look at -1. 1/3 to the -1 is 1/3 to the -1, which is 3. So if we put in x equals -1, what's y? Y is 3. So that's the point, -1, 3. So this graph is y equals 1/3 to the x. This graph is y equals 1/4 to the x. And if x is -1, if you plug in x equals -1 here, then you get x equals 4 for y. So the bigger the base, the faster it grows to the right if the base is bigger than 1. To the left, right, if the base is a fraction, 1 over the fraction, the bigger that, the faster it grows to the left. So 1/4, 1 over 1/4 is 4, so it grows like that. And it grows faster than 1/3 to the x to the left. Okay, so try to get Zoom to cancel this stop recording.